Hey, good morning, everybody. Can Learning Assistant please confirm that I can be heard? Anybody hear me?
Yeah, I hear you.
Okay, thank you. Someone asked on the chat if these lecture slides are available for download after the lecture. The answer is yes. There's a link on the Canvas homepage for this course. I have just one announcement, which is a repeat of what I made last time, which is that the second homework is going to be a regular length assignment, which will be longer than the very first assignment, which was on the short side. So please be sure you leave adequate time for it. Today we're going to talk about diffraction gratings and mention an application to chemical analysis. We'll talk about what Star Trek might have to do with the intensity of interference and diffraction patterns, what happens when we have both diffraction and interference simultaneously, and how big does a spy satellite lens have to be in order to identify things going on the ground. So I think last time we started talking about diffraction gratings. A diffraction grating works by sending light or having light sent through a large number of openings, equally spaced, and you get constructive interference when the distance that light from one slit travels compared to one just below it is equal to an integer number of wavelengths. And that's shown in this figure here. If you look at these little red lines here, those are the extra distances that light travels as it moves from one slit relative to its neighbor. And if that distance, which is given by d sine theta, where d is the separation between the slits, and theta is this angle shown here, which is equal to the angle towards the screen, when that value is equal to an integer number of wavelengths, then those two light rays will interfere constructively, and you'll get that happening for all of the light rays. They'll all be interfering constructively at that angle theta, and so you'll get a bright fringe. And the general expression is given by what's written there, d sine theta m equals m times lambda, and m here is called the order of the diffraction grating. If instead of that particular angle, you want to know the position on the screen far away where this fringe will occur, then you can use simple trigonometry to arrive at this formula that gives the position y sub m. Okay, so the higher the value of n, the narrower and the brighter are the fringes at all the different orders m. So what'll happen if, say, you simultaneously send two different colors of light at two different wavelengths, lambda 1 and lambda 2, into a diffraction grating. Let's say they're from lasers, two different lasers. So first, what is the central peak at theta equals 0 going to look like? And where do the higher order peaks from lambda 1 and the higher order peaks from lambda 2 appear? So the central peak at theta equals 0 is what you get when you set m equal to 0. The higher order peaks refer to m equals 1, m equals 2, m equals 3, and so on. And you can see from this formula down here that at m equals 0, we're going to get a value for theta that's equal to 0, independent of what lambda is. And at larger values of m, the value of theta will depend on lambda. So we can actually show a picture of what that'll look like here. So at the top, you see basically a single wavelength of light coming in and the pattern that it produces. So the m equals 0 pattern is the central maximum. So that's right here at an angle theta equals 0. And then at theta 1 over here, and at theta 2 down here, you see the first order, or the order m equals 1 and the order m equals 2 maxima respectively. And they're also labeled over here, and they're symmetrical on the other side. And each of these fringes is due to the wavelength of light going through and undergoing constructive interference. And what's nice about diffraction gratings is that most of the screen here is dark. As you can see by this picture, you only get bright fringes in a few places, a few locations on the screen. And so it's easy to distinguish where they are. And in particular, if you have two different wavelengths coming in, what you will see is at theta equals 0, so that's theta equals 0 right here, the two wavelengths, in this case there are two, overlap with one another. And so you get sort of this combined pattern of blue with purple, if you're sending in blue and purple light. But if you look over at theta equals 1, so here's theta 1, so this is the m equals 1 fringe, there are two different fringes close together, one from the purple and one from the blue light. And you can see that they're separated now. And that's one of the advantages of diffraction gratings and what it allows you to do. And I put together this little table here where I basically just solved this equation here for theta sub m. So I assume some value for the d, which is the spacing between the gratings. So if it's 600 lines per millimeter, you just take the inverse of that to figure out that the spacing is 1.6 microns, 1.67 10 to the minus 6. And then look at what happens when you set m equal to 0. If you look up here, here's the m that I'm changing. If I set that equal to 0, then I'm always going to get theta equals 0, independent of the wavelength. So the 470 is blue, and that's why that row is colored blue, and 400 is purple. That's why it's colored purple, the second row. And you see that they both come out at an angle of 0 degrees, which is what we saw over here. So they're both right on top of each other here. Okay, but then if we look at other angles or other orders, we get different behavior. So if we look at the first order for these two different wavelengths, 470 and 400, you see that the angles are no longer the same. They're not both 0 or both some other value. They're different. And they differ by just a couple degrees or so. And so at a faraway screen, a difference of a couple degrees in where the maximum is located due to this formula can give you a separation in the y dimension. So this separation between here and here that is visible. So it's sort of like a delta y there that is visible on the screen. So you can tell that there are two different wavelengths that are coming in, not by looking at the central maximum, because they're all on top of one another, but by looking at, say, the m equals 1 order, where you will see two fringes next to one another. For example, in this case, where the wavelengths of the light that we're looking at are quite close together, that means that the fringes will be close together on the screen. Okay, so let's work through this, this concept question. So what the concept question asks is, if you have a mercury lamp, which is shown in this figure here, so that's this thing here, it's this big black box. It basically has inside of it a glass tube that's evacuated except for mercury vapor that's inside. And then a high voltage is applied, which causes the mercury to get excited. And when the mercury gets excited, it emits light, and it emits light at a variety of different wavelengths. That light is then sent through diffraction grating, shown here. And when it emerges from the diffraction grating, it ends up on this screen back here. there's a sensor that is unfortunately in the way in this picture that just determines where the light is. And right now it's at the central maximum. And so you can see that it's basically seeing all the colors merged together. But the question is, what will you see if you look off of the central maximum for mercury light that is made up of, I should say, these 4 different wavelengths. And we're going to use a 600 line per millimeter grating, which means that there's a spacing of 1.6 times 10 to the minus 6, if I remember correctly, meters. So that's how you find D from that 600 lines per millimeter. So what do we expect to see on the faraway screen? Do we expect to see sort of a rainbow, a continuous rainbow of colors, one set of color bands, several different sets of color bands, widely separated lines of color, or a single swath of one color? So I've started the poll for you to answer that question. Okay, get your answers in, please. Okay, so most people answered C, which is the correct answer. So what you'll see is basically a pattern, and you can almost see it over here. If you look carefully enough, you can see sort of a green band right there, and there's kind of a purpley band just behind, mostly obscured by this, unfortunately, by this photosensor. And if you look really carefully, you can see some other bands over here, and there's even one over there and over there, which is at some larger angle. So these are at 90 degrees here. So the light is getting bent over and detected by that adjacent screen. But you can see that there are a variety of bands in each set. And in fact, what we can do is we can calculate where we expect those bands to be. So this is a very similar table to what I showed before, except now I've added the 4 different wavelengths that are relevant for mercury. And I've also added the distance that you would see these, where you would see these color bands on a screen that's like 20 centimeters away, which is roughly what that picture showed just a second ago in the demonstration that I showed you. So let's look at order m equals 1 first for these 4 different wavelengths. So there's purple, blue, green, and orange. And the angles are pretty close together, but certainly not identical. At the screen far away, well, far is just 20 centimeters, not all that far away, but you see that these bands are separated by a couple centimeters. In this case, the change in wavelength is large, so we get 8 centimeters difference, and then, whoops, another 2 centimeters of difference here. So you see that what this diffraction grating does is it takes these individual wavelengths and basically spreads them out and places them in different locations as different fringes on the screen that's far away. By the way, does anybody know what's going on down here why my spreadsheet failed to work in those two cases. You can put an answer in the chat if you know it. Excuse me. What do you think is happening down there? You can look at this formula here. That might help. I'll rewrite it here. D sine theta equals m lambda. And actually, if I move the D, I'm sorry, over to the other side, m lambda over D, what do you think will happen? That's right. We'll get out of the range of the arc sine. So theta equals the arc sine of m lambda over D. And for a given wavelength and a given separation between the slits, the distance, as that m gets larger and larger, eventually you're going to reach the point where this m lambda over D factor gets greater than 1. And when that happens, you can no longer take the arc sine. There's no angle, the sine of which is greater than 1, because the sine function is restricted to be between -1 and +1. So at that point, we can no longer solve this equation. And physically what that means is that the diffraction grating is trying, if the diffraction grating is sending the light this way, it's trying to send light at more than 90 degrees away from the forward direction, which means that it's not going to be visible. Okay, so some of the applications of diffraction gratings are in a field called spectroscopy. And this is such a powerful tool that spectroscopy is almost a field all by itself. It's a field where you measure the wavelengths of the emissions from atoms and molecules, and you determine what's in a particular sample, because every atom and molecule has a unique fingerprint of wavelengths of light that it puts out. And so you can, in principle, detect really small quantities of materials in large amounts of other materials by looking at for the particular light pattern fingerprint of the material you're interested in. So just as a random example, sodium emits two really closely spaced lines, makes two fringes that are very close together at 589 and 589.6 nanometers. Now, if you tried to see those by eye, it'd be hopeless. But if you have a sufficiently high resolution spectrometer, you'll be able to see two lines coming out, and they'll be right next to each other. But if the spectrometer is good enough, you'll be able to tell that you'll be able to resolve those two different lines from one another and say that, aha, I have sodium in here because I've got these two closely spaced lines, and they're at where I expect 589 nanometer wavelength light to be. So you can identify that there happens to be sodium in that sample. Okay, I'd like to now slightly switch gears and go back to talking about diffraction. So remember that diffraction grating, which we just talked about, is kind of a misnomer. It's really an interference grating. But now I'd like to return to the discussion of diffraction just briefly to talk about what happens when we take the geometry of a single slit and change it into a circular opening. So that's indicated up here schematically. So we've done in some detail what the diffraction pattern looks like from a single slit. And we have sort of a model for doing that, where we basically split up the slit into lots of little independent emitters of light. Trying to do the same thing for a circle is, substantially more complicated. And we're not going to go through that algebra and trigonometry. We're just going to take the result and use it. Circular openings are of interest because they happen quite frequently in devices that we build. So for example, sound waves coming from a circular loudspeaker are one example. Another more prominent example is light entering a telescope. So if you have sort of a handheld telescope, you know that at the end, it's got sort of a circular opening, and that circular opening usually has like a lens of some diameter at the end. And the diameter of that lens is the opening of the aperture of the telescope. In a similar way, larger telescopes typically consist of like a big circular mirror, and then the light that hits that mirror is focused on some small little camera. The size of that mirror is the aperture, or the opening effectively, of the telescope. And then similar statements can be made for microscopes, for example, as well. It turns out that the diffractive effects of the diffraction through a circular opening, if it's a circular opening on a telescope or a microscope or whatever, gives a fundamental limitation to how good a job these devices can do at resolving images, at figuring out, oh, there's something there, and right next to it, there's something else. Whether you're looking at a microscope or a telescope, you often want to do that. If you're looking at a telescope at stars, you want to be able to tell whether this blob of light is 2 stars or 1 star. And if you have good enough resolution, you can tell that it's 2 stars. Otherwise, you might be stuck and just say, well, it could be 1 or 2 stars. I'm not sure. So if 2 objects that you're looking at through a telescope or through a microscope are closer in angle than some value θ1, then their images will both overlap in the central maximum of the diffraction pattern. So, and then they'll be indistinguishable. So that's kind of shown here, just to remind you. So you can't really tell this is a circular aperture. What you see in this figure looks exactly like a single slit. We have a central maximum indicated here, and then we have sort of the brightest part of the image is this piece here. If there's another image far away and the light is coming through the circular aperture, and it produces a peak that looks like this, as it's just slightly offset from the other one, you won't be able to tell those 2 images apart, because the diffractive effects will make basically one large diffraction pattern in the center, and you won't be able to distinguish one object from the other, because their diffractive maxima will completely overlap, or very largely overlap. What you actually see through a circular opening is this pattern that's shown here. And let me just change this color back. What you see is out to this distance, this angular distance, this is θ1, everything falls into this central maximum. And so what you want is for that θ1, you want your objects, I should say, to be farther apart than that θ1 in order to be able to distinguish one from the other. Conversely, if you want to make that θ1 as small as possible, then what you need to do is make your aperture as large as possible. So D here is the diameter. There's this factor of 1.22 and the wavelength lambda. What this formula tells you is where this θ1 is that I drew here, or how big this θ1 is, for a circular opening. And it's got this weird 1.22 factor that comes up, and that's because of a lot of complicated mathematics. It depends on the wavelength. So the shorter the wavelength, the better you'll be able to resolve things. And D divided by D, that's the size of the aperture. So the bigger the aperture, the smaller that angle θ1, the easier it will be to resolve 2 images that are close together. Okay? So I'd like now for you to do this, this learning activity. I'm going to put you in breakout rooms in order for you to do this. So please, if you can, take a picture of this screen, because you won't be able to see it once you move into a breakout room. The idea is to estimate the opening or the size of the optics that's needed by a spy satellite. So if you imagine that the satellite is in low Earth orbit, which is about, for this problem, we'll say it's 160 kilometers or 160,000 meters. If we wanted to be able to read the letters on a license plate, which are, about 10 centimeters high, then how big does the aperture, or how big does the mirror have to be, or the lens that is on that satellite? So we're going to assume that the wavelength that's being used is 500 nanometers. That's sort of in the middle of the visible spectrum, so it's a good thing to use. And we're going to use this, this formula here that describes what the maximum angle two objects can be apart by in order to still be able to resolve them. And the one thing you're going to have to remember is the relationship between arc length, S, and distance and theta. And it's basically just that r theta is equal to the arc length. Okay? So I don't know if you can see that. I'll blow it up just temporarily. So the distance r, and usually they're the same, these two r's, times this angle theta gives you this arc length. And I want you to realize that the arc length and the straight line distance are going to be roughly the same in this case, because r is so much greater than s. Okay, so I'm going to now throw you into some breakout rooms. Hopefully this will work, and you can talk with one another about this, figure out how to solve this problem, and the LAs and I will try to help you out. Okay, I hope everybody's back in the main room now. So can you please put into the chat what you think the answer is here? How big does the optics have to be? What's the value of D roughly this satellite needs to have? Good, so a lot of people are getting 0.976 meters, about 1 meter. That's correct. So that's a pretty large mirror that you have to send up into space. And just for reference, the Swift satellite, which is actually run out of a building 2 miles west of a campus here, it's run by partly by the Penn State Astronomy Department, has a mirror on it that's 30 centimeters. And that was a very expensive NASA satellite project when it was launched. And here we're talking about, probably scales that are 3 or 4 times larger than that in order to have an effective spy satellite. So obviously NSA has a lot more money than NASA. Okay. So let me just now make some general conclusions about diffraction. So what matters is the ratio of the wavelength lambda to the slit opening. Or, the more generally, A can be considered the aperture opening. So that's why, in the past, it was a lot easier to see diffractive effects when people were looking at water waves as opposed to light. Because in order to get light to diffract, you need an opening, first of all, that's very, very small. It was pretty hard to make. And even if you were lucky enough to make one or you had it happen naturally, the light that went into that opening was rarely intense enough to be able to see the diffraction pattern that would come out through that tiny, tiny opening. There's not a lot of light can get through a tiny opening, obviously. So nowadays, it's not so hard to make these small slits. We can do that pretty easily. And we also have very intense light sources, lasers. So we can see diffractive effects and take advantage of them or compensate for them pretty easily nowadays. Generally speaking, the dividing line between having and not having diffractive effects is something like a millimeter or so if your wavelength is in the middle of the visible at 500 nanometers. So that gives you sort of the scale. Okay, so what I'd like to talk about now is intensity of interference and diffraction patterns. And the basic idea is that the light that's traveling through these slits ends up continuing after it's gone through the slits as traveling waves, and they meet at some screen far away where they undergo superposition. So it basically means we're just adding together each of these traveling waves at that point on the screen. And if you just think of 2 traveling waves, so a 2-slit experiment, then that superposition will have this form shown here of 2 traveling waves added together. Well, not traveling waves, the 2 oscillating waves added together with some phase difference. So the reason these are not traveling waves is because they've already traveled. We're asking what happens at this fixed point on the screen. A convenient way to represent this superposition is with something called phasors, and that's why there was that Star Trek reference earlier. And what phasors allow you to do is represent the individual wave. So E cosine omega t is one wave, E cosine omega t plus delta phi is another wave, as individual vectors. And the reason we can do that is if you imagine this vector here first, if you imagine that vector rotating around the origin in counterclockwise direction, just for argument's sake, and you think of its projection onto the x-axis, so just down here, this distance will be equal to E times cosine omega t plus delta phi. In a similar way, this vector here, if you take, or this phasor, if you take its projection down onto the x-axis, you get E cosine omega t. So those two vectors, those two phasors, when you project them down onto the x-axis, they give you E cosine omega t and E cosine omega t plus delta phi, respectively. And it turns out now, if you want to add those two time-varying quantities together, all you need to do is add these two phasors as though they were two vectors, and that's what's shown down here. And the resultant vector gives you the behavior of the sum of those two time-varying cosine functions. So what this basically means is that we then have this resultant vector rotating around the axis just like the other vectors were, but now it has a different relative phase, and it obviously has a different amplitude, because it's the sum of those two vectors, than the individual vectors themselves. So this may be a little bit fuzzy. I'll give you an animation in a second that hopefully will clarify things a little bit. But before I do that, the process of superposing two oscillating waves is just adding two vectors together with phasors. And if you do that, you will get the following two expressions. The first one is for the amplitude of the resultant wave. So that's this, this long vector over here. And that has an amplitude of 2e, where e is the amplitude of the original two waves, the two constituent phasors, times cosine of delta phi over 2. Where delta phi is the phase difference from one phasor to the other. So that's this delta phi. And then the intensity is the square of the amplitude. So we basically just square that quantity in order to get the intensity. So let me show you this simulation here of a phasor. So what you see is a mass hanging on a spring, and it's going to bounce up and down. And you know from physics 211 that that mass on a spring experiences a restoring force, minus kx, that causes it to undergo a simple harmonic oscillation, which can be described by a sine wave. And another way to depict that is graphically with this phasor, which is shown by that circle on the left of the figure that has a little purple line with a dot at the end of it. That purple line with a dot at the end of it is our phasor. And what that's going to do is rotate around in that circular path. And the projection of that phasor onto the y-axis, so you can project the phasor onto the x-axis or the y-axis. It's it's sort of a convention which one you choose. So in this particular figure, it's going to be projected onto the y-axis. That will trace out the motion of that mass bouncing up and down. And then if we plot that y value versus time, we'll get that sine wave shown on the right-hand side. So I'll start that playing. You can see what I described happening there. So you see that phasor is rotating around counterclockwise. Its projection onto the y-axis gives you the amplitude of the oscillation as a function of time. And if you then plot that amplitude, the y value as a function of time, you get the sine wave over on the right-hand side. So that's why this is called sinusoidal oscillation, simple harmonic oscillation. And down at the lower right, you see sort of a blow up with the various things labeled. So omega t is the angle at any given time t. So this phasor rotates around at a constant angular velocity omega. So the angle it has at any given time is just omega times t. the projection onto the y-axis is the amplitude, the length of the phasor times sine omega t. And then if you plot that versus, if you plot a sine omega t versus time, you get that nice sinusoid shown on the far right. Okay, so how do we use this sort of formalism? One thing you can do is you can add two phasors that have a fixed relative phase with one another. So these two phasors have a fixed phase. We take them and we add them together. Then what we get is what's shown at the bottom there. So to add two phasors together is just adding two vectors and getting the resultant vector. And this is mathematically equivalent to adding two time-varying sine waves that differ from one another by some phase. And you see that the amplitude is larger than the two waves individually. And you also see that it has some distinct phase relationship with the other two waves. So its trough is not at the same place as the trough of the other two waves. Okay, and then there's this figure here which sort of shows that a little bit larger. You can also understand maybe a little better constructive and destructive interference. So what's shown here are two waves and then their sum. And the sum is just the two phasors added together. If the two waves are perfectly in phase, which is what we see initially right here, then adding the two phasors means you have one phasor going like this and one phasor like that. They have 0 degrees between them because there's 0 phase difference between them. They're in phase. And then you get sort of the maximum interference between the two, the maximum amplitude. That's fully constructive interference. And then what you'll see as you follow this, this animation is that eventually it'll say, okay, what if we start changing the phase of one of these vectors, one of these waves with respect to the other. So now instead of having them with 0 phase difference where they're perfectly lined up with one another, you start changing the phase of one with respect to the other. And now the resultant vector is not, just vertical line straight up in this case, but it'll be, something smaller and smaller and smaller. And if these have the same amplitude and I end up having them 180 degrees apart, then they will completely cancel one another. We won't quite get to complete cancellation here because these two waves that are being added together, you can see the top two waves, the green wave and sort of the brownish one, don't have the same amplitude. So they're not going to be able to completely cancel one another, as you'll see. So now they're in phase. Then they start going out of phase. And you see that the amplitude is quite a bit smaller, and they'll go back into phase in a minute. Okay. So I encourage you to go and take a look at this animation afterwards if you want to study it more. And of course, if you have any questions about it, you should feel free to email me and ask me about it. Okay. Oops. So I want to do this concept question now, where we have a bunch of phasors, and we're going to use them to get an expression for the intensity when more than two waves are superposed to one another. So when you just have two waves, adding two cosine functions together is pretty easy. But if you want to add like 15 of them together, the trigonometry starts to get really, really painful. So there's an advantage to phasors, which particularly arises when you have multiple waves being added together. And one case where we have multiple waves being added together is through diffraction or light that's going through a diffraction grating. So imagine you have n wavelets. Those are just a colloquial term for waves. You have n of them produced by a single slit. Okay, and I'm just trying to make the poll here for you to answer. Hold on a second. If for some angle theta, we draw all of the n phasors. So You can see I've drawn all the n phasors together down here. And we line them all up like that. What angle, theta, that's this angle here, must we have chosen? So if we have a bunch of phasors drawn like this, what angle is implied in the for the light traveling through the diffraction grating? Someone asked if there's a way to change your answer after you've answered a question in a poll. Unfortunately, it's not like iClicker. Once you've made an answer, you're stuck with it. But don't worry about it. You're graded for participation, not for correctness. I wish it were the Zoom poll was a little more sophisticated. Okay, get in your answers, please. All right. So most people chose the answer A, which is the correct answer. So it's 0 degrees. And the way of thinking of this is when you draw all these phasors, in this case, they're all drawn horizontally, okay, like this, one on top of another. The relative phase between each of those phasors is 0 degrees. And that's what you get if all of the waves coming out of a slit and going towards the screen all have or have all traveled essentially the same distance in order to reach the screen on the other side. So there's no relative distance between these different these different rays traveling to the screen. Whereas in this case, there is a relative distance. It's this little blue line here, and that just keeps happening as you go down. In each case, there's a little extra distance each time, which causes a phase difference when the waves arrive at the faraway screen. But if there's no phase difference at the faraway screen, as indicated by this phasor diagram, then that means that the waves don't have any phase difference with respect to one another. And finally, that means that the angle that you're looking at must be 0, because that's the only angle at which that will be true. Okay, so if we get a little more complicated, and instead of using the angle 0, we have a slightly different angle, now there's going to be a distance, an extra distance traveled of each of the n waves relative to its neighbor. And so there's going to be a phase difference at the screen where they meet for the wave that travels from one opening versus the other versus the next one versus the next one. That phase difference will be constant. And so what you'll get is a bunch of phasors, okay, that have the same relative angle one to the next. So here's 2 phasors. And now I'm going to draw a third. That one will have the same angle with respect to the second that the second one had with respect to the first, and so on. And what you end up getting is a figure that looks sort of like this, where each of these vectors, these little e phasors, has the same angle with respect to the one previous to it. Okay, so maybe it'd be easier if these were drawn with a little greater angle. So this angle here is the same as this angle here, and so on. We keep getting the same angle of one vector, one phasor relative to the next. So in that case, we end up with a diagram that looks like the one shown here, and we can calculate the resultant vector to get what the superposed oscillating waves will look like at the screen. And if you go through the trigonometry, which is somewhat straightforward, a little bit involved, but I'm sure you can follow it through, you will get for a single slit that the intensity is some base intensity times the square of this sine function, sine of something over something, sine of alpha over alpha squared. If you then add on top of that single slit intensity, what you would get if you had two identical single slits side by side in a double slit experiment, so you get interference and diffraction together, that expression looks like this. So all that's been done there is to include this cosine squared factor, which I remind you came from back here. So it arose from adding these two vectors together, these two sinusoids or cosinusoids together, and then squaring the sum of the two phasors that represents them to get something that depended on cosine squared. So that's where that cosine squared comes from. And then what's in the argument there depends on the geometry that you've chosen. And this looks kind of complicated. And well, frankly, it's not trivial, but it actually has a relatively simple effect on the pattern that you see. And in particular, it causes patterns that look like this. So up here at the top, you see the light pattern that's, oh, sorry, I didn't realize it was this late. I apologize. Okay, I will stop right now and I'll see you next time. I'm sorry it went so long. If there are any questions, I'll stick around for a while. Thank you for letting me know. See you next time. Any questions? Feel free to ask.
I have a question. I was just wondering what lab is going to be like later today.
So typically you will meet at a fixed time. You will be assigned to work with 2 or 3 other people on the lab, which will obviously be virtual mostly, probably exclusively. And you'll probably run through some simulation together or use some data that was acquired by the lab TA and analyze that data.
Okay, and I saw on Canvas that the lab report was due tomorrow, but I have lab today, so I was curious if I upload it by the end of lab or tomorrow.
I'm not completely sure about that, so I think if you ask your TA or during lab, the TA will probably explain that. So you'll find out then.
Thank you.
You're welcome.
With this, these two intensity equations, what do the A, Y, and L, like what do those variables refer to in this situation?
So the A is the slit width, Y is the position on the screen, and L is the distance between the slits and the screen. It's the same, the variables that we used before for the 2 slit interference, it's the same nomenclature.
Okay, thank you.
You're welcome. If the diffraction grating moved at a significant speed horizontal relative to the wave source, would the interference pattern be influenced by Lorentz contraction? Probably. And you'd probably also have to worry about the Doppler effect as well on the light. That sounds like a complicated problem. I was just answering a question that was in the chat, in case you were wondering. Any other questions? Okay. Thanks, everyone. Have a good weekend.